Hello everybody and welcome back to another video. Today I'm going to be taking you through this problem. It's a double integral over a general region. So far we've only seen double integrals over rectangles. So here is our problem. We need to find the volume of the solid bounded above by f of xy equals 12 minus x squared minus 3y in the first octant. So I think the first thing to do here is go ahead and draw it graphically. So let's have here's our axis. And okay, so it's going to be parabolic in the x direction, straight line in the y direction, and then also parabolic in the xy plane. So this is what that looks like in the first octant. Let's also just draw in the intercept. So we've got 12, 4, and root 12 there. Okay, so, and we are asked to find the volume. So what we can basically do here is we can imagine that there is a square here, because we've only seen double integrals over a kind of a region like this, right? When the region is actually an irregular shape, in red here, right, it's bounded by this curved line, right, we kind of are struggling. So what we're going to do, we're going to imagine that the region keeps going, okay, and forms this kind of square, or no, it's a rectangle, sorry, not a square, my bad. And we're going to call that region, we will call that region R, and we'll call this region D, okay? So what we can say is we can define a new function, g of xy, which is simply f of xy, right? Where f of xy when, sorry, hold on a second. Yeah, f of xy, so it will equal f of xy if if that point in the xy plane is in the region D. And then but otherwise, if it's in this area here, so if it's in R but not D, it's 0 otherwise. Okay, just gonna get rid of that. Sorry, stupid. Oops, wrong pen. Actually, you know what? Actually, no worries. Okay, so hopefully that makes sense. So we've defined this new function g of xy, and now let's go ahead and, well, we know Fubini's theorem, and that any region over a rectangle like that, we can use iterated integrals. So let's go ahead and do that. Okay, so we can say that the double integral over D, right, f of x, y, dA is equal to the region over R of g of x, y, dA. So hopefully that makes sense given this graph above. So now we're just going to go ahead and compute this. So let's go ahead and just get this done. In fact, you know what? Let's draw another graph just to help us here. Let's just go ahead and draw another graph. So remember, parabolic in this direction, in the x direction, straight line in the y direction, and then, oops, that's not good. And then also parabolic in the xy plane. Here we have z, we have y, and we have x. And let's just put in the intercept. So root 12 is the x-intercept, 4 is the y-intercept, and 12 is the z-intercept. Okay, so here we have the shape again. And we have, okay, and we are basically now computing this integral, where r is obviously this, this square that we drew above. So let me just highlight that. Okay, so that's what we're computing. And how do we do that? Okay, so it depends if we want to do it with respect to y or x in the inner integral. Let's go ahead and integrate with respect to y in the inner integral. So we're going to keep x constant. So let me just draw this graphically for you guys. Let's do it in green. So we're going to keep x constant, right? And we're going to do like a sort of, I guess you could call it like a cross section, okay? We're going to find this area and we're going to imagine, right, it's kind of shifting through this shape in the x direction. Okay, but this is the integral and we're keeping x constant. So I'll just say here, fixed x. So let's now set that up. We've got, so let's do that in integral. We're differentiating with respect to y. What's the original equation? 12 minus x squared minus 3y. So, okay. So 12 minus x squared minus 3y dy. And that's going to be, okay, so that's going to be from, that's going to be from 0, okay, because y starts at 0, to whatever y is determined by this, this line here. Okay, so this line, let's just solve for that. Okay, so 12, okay. So we're going to set this equal to 0 because this is defined when z is equal to 0. So 12 minus x squared minus 3y equals 0. And now we just have to rearrange to make y the subject. So we're going to say, okay, 3y equals 12 minus x squared. So y equals 4 minus a third x squared. Okay, and that is therefore going to be our upper bound here. 4 minus a third x squared, right? Because y, it goes from 0 to whatever y is defined by this line here. So that's going to be our inner integral. Let me just highlight that. Okay, so this is our inner integral. Now we're going to do our outer integral. Okay, so our outer integral is going to be integrating with respect to x, so dx, and it goes from 0 all the way to root 12. So 0 is our lower bound, root 12 is our upper bound, okay? So this is basically our final integral that we now need to evaluate. So let me just write that out again. Root 12, 0, 4 minus a third x squared, 0, 12 minus x squared minus 3y dy dx. Okay, now what do we do? Okay, so let's first integrate that inner integral, evaluate that inner integral with respect to y. So x is going to be a constant here. We've got 12y minus x squared y minus 3 over 2 minus 3 over 2 y squared. Just going to check that's right. Yeah, I'm happy with that. And we're evaluating that over 4 minus a third x squared and 0. Okay, so this is our inner. Let me just put that here. So this is our inner. Okay. So let's go ahead and plug it in, plug these bounds in. So we get 48 minus 4x squared. And then we've got, let's just make sure we get the signs correct here. Minus 4x squared minus 4x squared plus a third x to the 4. And then our final one is minus 3 over 2, 16 minus 4 over 3 x squared, so multiply by 2, so minus 8 over 3 x squared plus a ninth x to the 4. And then it's minus 0 because there's y in each of these terms. That's just going to equal 0. So this is our final thing here. And let's just now simplify that. So minus 4. So, okay. So 48 minus 8x squared plus a third x to the 4 minus 24 plus 4x squared minus a sixth x to the 4, which is equal to, sorry about this guys, this is a little bit of a pain, 24 minus 4x squared plus a sixth x to the 4. Okay, that's it. Now we're going to integrate that. So that's our final expression. We're going to now put that into our outer. So let me just do this. Outer. So we're going to integrate, we're going to evaluate this integral. I hope I've got the signs correct here, guys. I really do. From root 12 to 0. Okay. In the comments, let me know if I've made a mistake here, guys. Okay. So let's go ahead and do this as we get. Oh, and we're integrating with respect to x, obviously. Okay, so we get 24x minus 4 over 3x cubed plus a 30th x to the 5. And we're evaluating that from 0 to root 12. Okay, so look, all the terms contain x, so the lower bound expression is just going to equal 0, so we just have to evaluate the top. So it's going to be 24 root 12 minus 4 over 3, 12 root 12 plus a 30th. We're going to have 12 times 12, 144 root 12. Okay, so let's go ahead and get this done, simplified. 24 root 12 minus minus 16 root 12 plus 144 over 30. Just gonna get my calculator out there with me. You probably don't need a calculator, but I'm feeling lazy. 144 divided by 30. So that's 4.8. Well, you know what? Actually, I don't need that calculator. I can do this myself. So 144 over 30, which is 72 over 15. I don't think that goes any further. 144. Yeah, I mean, yeah, 72. Or is no 72 is divisible by 3, I believe. How many times? 24. Okay, so it's 24 over 5. I think, yeah, that's correct. Yeah, okay, I'm happy with that. Root 12. Okay, so the final answer is 8 root 12 plus 24 over 5 root 12. Or, to put it maybe a little bit better, nicer, we can say that's equal to, so 40 over 5, so 64 over 5 root 12. There's our final answer. Hope you enjoyed this video, and yeah, maths is great. I could have made a mistake in that. Let me know in the comments if I did. But yeah, that was quite long. But you get the picture, right? All we did here is we imagine that there was here, instead of this irregularly shaped region, there was this kind of rectangle, and then the rest is fairly simple. And I guess the only hard part was rearranging the equation to for y to be the subject, so that we could get the upper bound of this in integral. But aside from that, fairly basic, but definitely long, although I could have made a mistake. So as I said, let me know.